we'll have Bojan Bašić and Ben Young. So in this order. So I will start with Bojan Bašić. So Bojan is a professor at the University of Novi Sad in Novi Sad, Serbia. He has been with us, an instructor at this camp over the last 2 years. In fact, he's been here at this camp 3 times, but the first time he was the leader of Armenia, right? If I remember correctly, one of the leaders. So, and after that, we decided to bring him as an instructor to the camp. So, ladies and gentlemen, let's give him a big welcome to Bojan Bašić.
Thank you very much. Do you hear me well? Okay, great. So this is, if I'm counting well, this is your 5th problem from IMO that you will see in scope of those lectures. And I don't know, do you have any information about how those problems were chosen by us instructors? Basically, every instructor had the freedom to pick any problem he wants to present. The only condition was that 2 instructors cannot pick the same problem. Actually, even that was not explicitly stated, but I guess it was clear that it made no sense. But apart from that, every instructor had a complete freedom, and that gave me quite a terrible headache. So I was thinking for quite a long which problem should I choose, because it's not really easy to make such choice. There are many students here. There are many students here, many leaders. Some of you are stronger students, some of you are a little bit weaker. If an instructor chooses some hard problems, maybe weaker students would not be able to follow. If an instructor chooses some easier problems, then maybe some students will be bored. And in fact, that's not the only issue. There is also the following problem. If we choose some problem that is interesting enough, then there are high chances that you have already seen it. So if it is interesting, then you probably know about it. And what can we present then? And if we choose some problem that's boring, well, it's boring then. So after thinking for quite a lot, I decided to choose this problem. It was problem 3 from IMO 1990. And the reason for that choice was not that I find the problem particularly nice, nor particularly ugly. I don't think it is too hard. I don't think it is too easy. But the main motivation for my decision was that this problem is somehow connected to various fun facts about IMO. And while presenting this problem, I will also misuse the opportunity, misuse this time that was given to me to present also some interesting facts that you probably do not know about IMO. In general, I am fan of various quizzes. And there is one quiz that I presented to various participants of very first IMSC here in Beijing 2 years ago. And not only in Beijing, but okay, let us focus on that. And the quiz says like this. I will give you a list of 5 words. There is exactly one of those 5 words that have never appeared in an official IMO problem statement. So the words are composite, dodecagon, graph, radian, and vector. So 4 of those words appear in IMO problem statement, 1 did not. Okay, maybe we can even make a vote. Who thinks that the word composite never appeared? Okay, who thinks that the word dodecagon never appeared? Okay, who thinks that the word graph never appeared? Okay, who thinks that the word radiant never appeared? And who thinks that the word vector never appeared? Okay, so it seems to me that there is like a tough call between radian and vector, if I counted well. Well, the truth is as follows. So dodecagon appeared in 1977, problem 1. Graph appeared in 1991, problem 4. Radian appeared in 1984, problem 3. And vector actually also appeared in 1973, problem 1. So all those words look like something that's not really expectable from IMO problem statement. For example, graph. There were many IMO problems about graphs, but they are usually phrased like you have a road between cities and whatever. But in 1991, problem 4, you may check, there was indeed a problem that says, given a graph G, then something blah, blah, blah. And that leaves the word composite, which never appeared in an IMO statement. So that may be very improbable and hard to believe, but it is so. You may check if you want. But remember that this was a quiz from 2 years ago. Because after that happened IMO in Japan, and then problem 1 in IMO 2023 unfortunately destroyed this quiz because it says find all composite integers such that blah, blah, blah. I am actually very sorry because I was present at that IMO, but I missed that meeting where English language were polished, English language version of the problems were polished. So if I were on that meeting, I would say this. It's not really a mathematical argument against stating the problem this way or that way or so on, but I would say this argument because it's so unbelievable that for 63 years the word composite never appeared, and maybe it was not necessary to break that tradition, but what's done is done. Okay, so since this quiz is not adequate anymore, here's another quiz for you. Okay, I will give you a list of some IMO problems. All of them have something in common. The only one is an exception. Okay, and you have to find which problem is the exception and what makes it an exception. And the list is this thing. So 1993, problem 3, 1999, problem 4, 2001, problem 5, and 2018, problem 3. And if you need some hint for this, a hint is you can also add problem 4 from Balkan Mathematical Olympiad 2012 to the list. I mean, it's not from IMO, obviously, but if we ignore the fact that it is not from IMO, if you add it, it is still the case that all of them have something in common, with the exception of only one. Okay, so I won't tell you the answer right now, because the main point of this lecture is to present some problem and its solution, so let us, at least so far, move to what we are actually supposed to do today. So the main topic today is IMO 1919, problem 3, and the statement says like this. So we have to find all integers greater than 1 such that this is an integer, or that 2 to the power of n plus 1 is divisible by n squared. Okay, so this is the problem. Let us see its solution. The solution goes like this. Okay, clearly n is odd because it divides 2 to n plus 1, which is odd. We choose the least prime divisor of n. Let us call it p. And then we have the following conclusions. So p divides n, and therefore p also divides n squared. And n squared divides 2 to n plus 1, because that's the statement of the problem. And 2 to n plus 1 divides 2 to 2n minus 1. You can get this by factorizing, for example, the term on the right. Okay, and what else do we have about divisibility by p? We also have, of course, by Fermat's theorem, that p divides 2 to p minus 1 minus 1. And now from those two conclusions, we have that p divides 2 to the power of GCD of 2n and p minus 1. So this is actually a well-known fact about powers of 2. And can we say anything about this GCD? Well, recall that p is the prime divisor of n, which means that we can take these two out. N is odd, and since p is the prime divisor of n, then n and p minus 1 are co-prime. P is the least prime divisor, that's why they are co-prime, which means that this GCD equals 2. And now, when we take into account those two conclusions, so p divides 2 squared minus 1, which means that p has to be 3. Okay, so the conclusion here is that the least prime divisor of n equals 3. Okay, now what? Well, now let us write n as 3 to some power times some d, which is not divisible by 3. We know that k is at least 1 because of the previous slide. And now let us consider this expression, 2 to n plus 1. We can write it like this. And this can be factorized like this. Okay, so everything clear so far? Okay, so we now have these 4 lines of text. So consider any summand from these large brackets. Every summand is congruent to -1 to the power of I, which means that every summand is congruent to either plus or -1 modulo 3. But there is an odd number of summands. There is exactly these summands there, which is an odd number, which means that that sum altogether is non-zero modulo 3. Therefore, the conclusion is that this whole parenthesis is not divisible by 3, which means that the larger power of 3 that divides 2 to n plus 1 is the same as the largest power of 3 that divides this thing here. Okay, so let us now calculate the largest power of 3 that divides this thing here. Well, for that, we can use the following lemma that says for any non-negative integer k, we have that 3 to k plus 1 divides this thing, but 3 to k plus 2 does not divide that thing. Okay, we can sketch the proof. The proof is, as it says, induction on k. What do exactly mean? That is, how do we perform the induction? Well, the base case is, of course, clear. If we put k equals 0, we get 3 divides 3, and 9 does not divide 3, which is fine. And then we can make this inductive assumption that 2 to 3 to k plus 1 is divisible by 3 to k plus 1, or 2 to 3 to k is 3 to k plus 1 times something minus 1, where this something, which I denoted by A, is not divisible by 3. Then, for the inductive step, we have this thing. So 2 to 3 to k plus 1 is this thing cubed, and then plus 1. And when we cube this thing and calculate the expression, we get this thing, which is clearly divisible by 3 to more than k plus 2, plus this thing, which is divisible by 3 to k plus 2, but no more than that, which altogether means that the whole expression is divisible by 3 to k plus 2 and not divisible by 3 to k plus 3, which finishes the inductive step. Okay, so now we know that n is divisible by 3 and not divisible by none. So we have now this. We have that 3 to k plus 2 does not divide 2 to n plus 1. And we have that 3 to 2k divides n squared, which in turn divides 2 to n plus 1. Altogether, we conclude that 2 to k is less than or equal to k plus 1. Because, look, the right-hand side here and here show the same expression. That expression is divisible by 3 to 2k and not divisible by 3 to k plus 2, which means that 2k has to be at most k plus 1. But what is the only way that 2k be less than k plus 1? The only possibility is, of course, that k equals 1. So now we get that n is 3d, where d is something not divisible by 3. And let us now try to make some conclusions about d. So our aim is actually to prove that d equals 1. So that the only solution is n equals 3. Let us suppose that d is larger than 1. And we take q to be the least prime factor of d. Now we shall have a few lines here, and you may actually compare them to the argument from 2 slides ago. It will turn out that whatever we did 2 slides ago, we do now like completely the same. Only slight adjustments are needed. So we take, remember at the first slide we took p to be the least prime factor of n. Now we take q to be the least prime factor of d. Then we have q divides n squared divides 2 to n plus 1, and 2 to n plus 1 divides 2 to 2n minus 1. And also q divides this thing by Fermat's theorem, which altogether means that q divides 2 to GCD of 2n and q minus 1 minus 1. And we now try to conclude something about this GCD. So we can take 2 out. So GCD of this is 2 times GCD of n and q minus 1. And what is GCD of n and q minus 1? So q is the least prime factor of this thing here called d. If this GCD was something, for example, if there were a prime dividing both n and q minus 1, the problem is that that prime cannot divide d, because q is the least prime factor of d. Nothing less than q can divide d. But there still exists a prime that divides n and does not divide d, That's the number 3. So in case that q minus 1 is divisible by 3, it is possible that this GCD is 3. And there is also a possibility that GCD is 1 if q minus 1 is not divisible by 3. So altogether, this GCD is either 2 or 6. Twice this GCD is either 2 or 6. Okay, and so when we plug this here, if the result is 2, then we have that q divides 2 squared minus 1, which means that q is 3, which is impossible. Q is not 3. We proved that n is divisible by 3, but not by 9. And if this value is 6, then we have that q divides 2 to the 6th power minus 1, which is 63. And as we again recall that q is not equal 3, that leaves only one possibility, that q is 7, sorry. But now, therefore, n is divisible by 7. N divides 2 to n plus 1, which means that 2 to n is congruent to minus 1 modulo 7. And we finally reach a contradiction here, because if we look at all the possible remainders of powers of 2 modulo 7, we shall easily see that all the possible remainders are only 1, 2, and 4. So 2 to any power cannot be congruent to minus 1 modulo 7. Therefore, we have a contradiction here, which means that this assumption that t is larger than 1 is not true, which means that d has to be 1, and the conclusion is that the only such integer is n equal 3. Okay, so this solves the problem. And I will return to the initial slide for a moment, because I forgot to say one thing here. So I was telling you how I was thinking a lot of what to choose and what are motivations for this or that choice and so on. And this thing that's written down there, Beijing, China, it's not the place of, it's not written there because of that IMO, but because this summer camp is held in Beijing, China. But it's a complete coincidence. So after I chose the problem, it turned out that this was exactly the place where that IMO was held. So that's a kind of a sign that, okay, the choice made sense. And one more coincidence is that the problem was proposed by Romania, and you probably noticed that Romanian instructors quite dominate here. So all of those are signs that hopefully the choice was adjusted. Okay. We all solved this. Okay. So we solved the problem. So what are we going to do next? Well, let us now move some 9 years in the future. Although the title says blast from the past, but we move into the future. So we look at IMO 1999, where the following problem appeared as problem 4. So we have to find all pairs n p of positive integers such that p is prime, n is less than or equal to p, and p minus 1 to the power n plus 1 is divisible by n to p minus 1. Well, it turns out that this problem can be solved even without this red restriction. So assume that we are looking all the pairs that satisfy only the first and the third restriction. Okay, so let us see some key steps of that solution. We won't go too much into details because this was not the central problem for today, but let us see at least some key steps. Okay, So let us make the assumption that n is greater than 1 and that p is odd, because if it is not, we check and actually get some trivial solutions, but they are not interesting. It can be shown, which we won't do today, but it can be shown, and it's not really hard, that n has to be divisible by p. So, okay, n is divisible by p, great. And we then write n to be p to k times d, where d is not divisible by p, and k is at least 1. And we have the following lemma. It says for any non-negative integer k and any odd prime number p, we have that p to k plus 1 divides p minus 1 to p to k plus 1, but p to k plus 2 does not divide p minus 1 to p to k plus 1. So does this lemma look familiar to you? Yes, why? Sorry? So actually, I don't see who am I talking to.
It is the lifting the exponent theorem. Yes, lifting the exponent theorem.
Actually, yes, things like this are known among students from IMO circles are as lifting the exponent or something like that. But I intentionally did not want to mention any of those fancy theorems today, except for Fermat's theorem, because that one was unavoidable. But everything else I wanted to do in completely elementary manner. So this lemma is actually, you may compare it to the lemma we proved a few slides ago. And that one from a few slides ago is actually precisely the special case of this for p equals 3. And this is for general p. And the proof for general p is actually exactly the same as the one you saw a few slides ago. So no difference basically at all. So if you know how to prove that, you also know how to prove this. And okay, assume now that we proved this lemma. Then we want to write this thing p minus 1 to the power n plus 1. This is the expression that appears in the numerator of that fraction that we want to show that is an integer. So we write this as p minus 1 to p to k to power d plus 1. And then we factorize this and obtain this times some d. For this d, we can show that it is not divisible by p, which means that the largest power of p dividing this is the same as the largest power of p dividing this. And the largest power of p dividing this by the lemma is p to k plus 1. So this left-hand side is divisible by p to k plus 1 and not divisible by p to k plus 2, which altogether means we have that p to k plus 2 does not divide this, and we have that this thing, p to k times p minus 1 divides n to p minus 1 because p divides n, p to k divides n. And finally, n to p minus 1 divides this thing because that was the requirement of the problem. So altogether, from those two conclusions, we have that k times p minus 1 is less than or equal to k plus 1. And this seems to leave a very limited choice of options. Actually, if k is at least 2, then this thing is already too large. So the only option is that k is 1 and that p is 3. And that means that once we know that p is 3, if we plug p equal 3 in that statement, we basically have to find all n's such that n squared divides 2 to n minus 1, which is, as you may remember, problem that we solved today. And not only that we reduced this problem to the previous one, but also all those steps from here, so from the lemma and everything after that, are completely the same. So it does not really make any difference whether p is 3 or p is whatever. Basically, the only thing that's different here is how we show that p divides n, which we skipped in this presentation, but that's the only new job that we have to do. Okay, so remember there was some quiz in the beginning. So let us recall what was the statement of the quiz. So we have those 4 problems, or 5 if you count also the BMO. And we had to find a problem that's different from other problems in some sense. Okay, so among those 5 problems, you now know what the statement of problem 4 from IMO 99 is. That's the problem that we just saw. And we now know that this problem, with the second bullet point, actually, in a way, incorporates a problem that appeared before it, that had appeared somewhat earlier. It actually appeared precisely at the IMO, but still, although it incorporates that problem, there is at least some novelty. Okay, so that's the story about this problem. But what about the other problems from this list? Okay, so this is the statement of IMO 1993, problem 3. We won't read this completely, but you have the statement there. And actually, this was the statement of the problem from All Soviet Union Olympiad in 1992. So that was 1 year before. And it turns out that so problem 4 from IMO 99 does incorporate something from before, but it still has some novelties. It turns out that this problem from 1993 actually is completely the same as the problem that appeared 1 year before, but it went completely unnoticed. It actually, it's even special case, because I don't know how many of you can read Russian, but basically the statement is completely the same, only we have m times n board here, and in IMO it was n by n. So the bottom problem is more general. From IMO 2001, problem 5, this was the problem. And what is also interesting, the following problem appeared in a magazine called Crux Mathematicorum in January 2000, which you can again see that it is completely the same as the previous one. Actually, there is a given that the angle 60 degrees is in IMO problem, which is again a special case. Such requirement is not given down there. And actually, all those statements are precisely screenshots of the original statements, because not because I was lazy to retype them, but I wanted to make them as accurate as possible. And what about problem 3 from IMO 2018? So you probably know this one. It's quite a famous problem about anti-Pascal triangle. So this one actually appeared in a scientific paper all the way back in 1977, where anti-Pascal triangle was called exact difference triangle in that terminology. And it was proved like 40 years ago before this problem that such triangles do not exist. And finally, problem from Balkan Mathematical Olympiad in 2012, problem 4 was like this. Exactly the same problem appeared on USA Mathematical Olympiad like 4 days before BMO, literally 4 days. This was, I think, April 28, and this was April 24. However, what I want to say, I do not want to criticize anybody. So I actually know many people from Problem Selection Committee, and I know how hard they work. But simply, people cannot know everything. Problem Selection Committee works very hard. Jury at IMO works very hard. But sometimes things get unnoticed. So this is just like a curiosity and not my intention to criticize anything, because I indeed like IMO very much, and all that story about high school competitions, I would not be here if it were not that way. And that's why I actually like to collect various curiosities about IMOs and other competitions. So this was something from such my collection. And it can be actually that at least some of those things are really coincidences. Actually, I believe that most of them, if not all, are coincidences, because there is one of maybe my favorite coincidence about a problem that appeared on IMO, which looks completely unbelievable. So this was problem 2 from IMO 1994. It has a rather long statement, but the point is, prove that some line is perpendicular to some other line if and only if some 2 segments are congruent. Okay, nice geometry problem, one would say. The story how this problem appeared on the paper is very, very interesting, because it turns out that Australia was proposed the if part for the shortlist, and Armenia was completely independently proposed the only if part. And then the Problem Selection Committee noted that they could combine those 2 proposals in one problem. So imagine what a coincidence that is for the same year. That happened in the same year. And finally, there is one more slide. So we have already mentioned IMO 2001. That was one where that problem appeared, one of those problems that appeared at IMO and that appeared earlier in some other source. IMO 2001 is actually, in my opinion, maybe the, maybe the quirkiest, let me use that word from the title. Like, that problem that was repeated was not the only funny thing about IMO 2001. Actually, there were many different fun facts about IMO 2001. Okay, so we have that problem that was repeated. There was another problem, C5, in the shortlist, which is completely the same as one problem from 1983 long list, because back then, in 1983, long lists were used to be published. So every proposed problem was made public, and now only problems for the shortlist are public after 1 year ban. Okay. Then let us look at the following problem from the shortlist of IMO 2001. So it looks like an interesting number theory problem. So we have some positive integers. We have some equation between them. And we have to prove that AB plus CD is not prime. So this is the exact statement how the problem appeared on IMO, in shortlist. Do you see any more natural way to say the last sentence? So for some reason, the word composite was really, really expected here. But yet, for some reason, the problem says prove that AB plus CD is not prime. It is almost like it was intentionally avoided to keep that quiz from the beginning. I mean, it's not. Nobody really cares, except for me maybe, whether the word composite will appear or not. But it was very close if this problem were chosen for IMO. Remember that we are still talking about shortlist here, but it was very close to that composite appears here, and for some reason they stated as not prime. Then another fun fact about that shortlist is there are 6 number theory problems in that shortlist, which is actually a little bit lower than expected, but never mind. So 6 number theory problems on the shortlist, and 2 of those 6 have purely geometric solutions. I mean synthetic geometry, like not some integer points in the lattice or something like that, but real geometry in 2 different number theory problems in the same shortlist. And finally, one more fun fact is there was one streak that I find quite interesting, and IMO 21 is a part of that streak. So there exist 4 consecutive years, that's from 1991 to 2002, such that in each of those years, a shortlist contained a problem that can be solved by reducing it to some Pell's equation. So in 1999, it was N3, in 20 it was N5, in 21 it was N2, and in 2002 it was N4. Of course, theorems about Pell's equation cannot be part of the official solution, or at least not of the unique official solution. They can be part of some alternative solution, but I find it interesting that there were 4 consecutive years such that in each of them, those students who know Pell's equation can solve the problems easily. Okay, so that was 45 minutes, and that's all for me. Thank you for your attention.
All right, if we have any questions for our speaker. Any questions, please raise your hand so I can see you. Okay, if there are